and experimental reactor design. The early 1950s was an interesting time for reactor development in the USA. Various different designs were explored as scientists probed reactor behaviour. Our story for the borax begins with an interesting event, an operator error-induced excursion at a test reactor in the Argonne laboratory in Illinois. The heat generated boiled off the moderating water, and although splashing 4 operators with some spicy reactor soup, nothing really dramatic occurred. This sparked the idea that maybe a reactor moderator could be kept in a stable boiling mode. An experiment was put forward and it was greenlit, but not to be run at the Argonne National Laboratory. Instead, a site a bit more isolated was put forward, as it was considered to be a little bit of a risky experiment. But why bother with a boiling water reactor? Well, potentially a boiling water reactor offered some advantages over, say, a pressurized water reactor. One of the main benefits is not needing as strong of a reactor vessel, as the pressure of boiling water is below that of a pressurized water reactor. Another advantage, at least in theory at the time, is that this type of reactor is self-regulating. Okay, let's quickly talk about this. You see, in order to sustain a chain reaction within a reactor, you kind of need a moderator. And in a boiling water reactor, this is like water. If you begin to remove a reactor's control rods, the reactivity increases. This generates heat, so much so that it begins to boil off the moderator. As it turns to steam and loses its characteristics as a moderator, which then reduces its neutron slowing abilities, it in turn reduces the reactivity, and thus heat. In turn, the steam cools down and turns back into water, increasing its moderating characteristics. With greater moderator density, the reactivity then increases. Basically, the reactor will self-regulate through the boiling and cooling of the water to a point of stability. This makes the concept very safe and importantly very predictable, which is ideal for power generation. This is the rough concept. I hope I explained it right, and it was the rough idea that in 1952 the Argonne laboratory wanted to test out. The borax's name came not from boronic acid, but instead from boiling reactor experimental. It was a fairly basic design, omitting any power generation capability, and instead of condensing the coolant, moderator for reuse, it would just evaporate to atmosphere. Coolant was also circulated naturally through free convection. The reactor was constructed in sections at Argonne and shipped in the spring of 1953 to be put together like a puzzle at the National Reactor Testing Station in Idaho, not far from the EBR testing area. The reactor vessel was placed in an earth mound inside a shield tank. Above this was the control rod drive carriage, which had the mechanism for inserting and retracting control rods, of which there were 5. This was the main means of reactivity management for the borax reactor. The reactor held roughly 100 litres of demineralised water. The fuel assemblies were enriched uranium placed in thin concave aluminium plates. The plates had gaps between them to allow the coolant to flow between. Operators from both Argonne and the EBR would staff the new reactor, which was operated from a mobile trailer located around a half a mile from the test site. The experiment begins. The reactor went into operation and was planned to be run during the summer months of 1953. After initial criticality, the first tests were rather boring, in the sense that they were similar to any new reactor. A few short power tests were undertaken. These were to push the reactor coolant close to boiling point. Due to the potential for release of reactivity, staff were evacuated from the area during the runs. Next came a series of transient tests to probe the limits of stable operation. This was achieved by exposing the reactor to power surges. The tests were seen in this rather spectacular video, ejecting spicy water out of the open reactor tank, reaching an estimated power level of 70 megawatts in just a few milliseconds. The reactor test went rather well, helping to prove the concept of the boiling water design. However, the actual reactor test unit had quite a few issues. Due to its prototype nature, welds were rather weak, allowing water to leak out. Eventually the tests had to end towards the end of the summer, as the reactivity between the increased power test runs resulted in personnel difficulties, in that manipulation of fuel resulted in operators getting very close to their daily exposure limits. The tests would be shut down over the winter, during which time the Borax 1 reactor would be rebuilt with improvements to its control gear, in the mobile control room, and to its rod assemblies. By the summer of 1954, the reactivity of the reactor had decayed sufficiently that fuel elements could again be manipulated manually. The new and improved Borax was given the number 2 designation. By this point, Borax 3 was also in the works with an improved reactor vessel that could take higher pressures. So after some more experiments with the two, the scientists thought about maybe something for the lulz, a good old reactor bang. The testing throughout the summer worked on runaway situations to establish the upper limits of stable boiling operation. But finally, the Borax 2 would reach the end of its life of being non-ungrenaded. The destruction. So in order to go boom, the Borax 2 needed some modifications. This was mainly with a strong spring that, when the control rod being held in place by an electromagnet, which was switched off, would shoot the control rod out of the core, causing the reactor to go prompt critical almost instantly. The destruction test was set for early morning in March. Leading up to a 7 AM start, a short, low-power transient test run was undertaken to verify that the reactor equipment was working, after which operators conducted an inspection of all the control rods. During this time, a fuel assembly was found to be deformed and had to be replaced. The test was reliant on wind direction, as the released material post-explosion could travel towards any waiting onlookers. In order to decide whether to go or not, smoke bombs were set off to indicate the wind direction. Operators made the final checks, and the high-speed and still cameras were put into action. The reactor was brought up to a steady state low power level, ready to begin the destruction. The time was around 8 AM. The control rod electromagnet was switched off, shooting the control rod out of the reactor via the strong spring and the power of good old gravity. Quickly, the reactor power spiked. An explosion followed, lifting the entire shield tank out of the core and shooting it into pieces over an acre of the surrounding area. The control rod assembly shot into the air, being flung back to Earth by the cabling that was used to electronically control it. Steam, water and fuel debris scattered out. Pieces of molten fuel rained down in the surrounding area. A cloud of radioactive steam and vapour moved southwards from the reactor site. Only the reactor vessel's bottom plate remained in the pit. The rest had been resited in a debris field amongst the desert sand. As soon as it was deemed safe, roughly by the end of the day, staff in protective clothing went in to inspect the damage and take photos of the remaining mangled machinery. The test had been a success, a very entertaining and messy success at that. But like all fun things, the boring part of cleaning it all up had to be undertaken. The aftermath. Debris from the reactor was examined and documented. Any non-fuel debris was placed within the old dugout that was used for the reactor vessel. Cleanup crews sent any found uranium fuel off for reprocessing,